In this discussion, we're going to talk about how a wave propagates through a dielectric when we're looking at plane waves in phasor form. And the key thing is to note that is to relate the fact that if the permittivity epsilon ends up being a complex number, meaning it has an imaginary component, that relates to conductivity and loss. So one way to view conductivity is, even though we associate dielectrics with this epsilon term, usually with dielectrics it's mostly real epsilon, but if you have an imaginary part of your epsilon, so if your epsilon is a complex number, that imaginary part results in propagation loss, and we can also tie that to our current concept of conductivity. So let's jump right in. Let's start with our definition of the wave number. So remember that with our phasor form, we have our propagation number k, which is in units of radians per meter. So in our phasor form, we had this. For a wave propagating in the positive direction, we have a minus jkz, where k tells you the amount of phase that changes per unit meter in the z direction, right? So now let's define this jk as a complex number. So let's say jk is equal to alpha plus j beta. Now these alpha and beta terms are not arbitrary letters. These are actually these are characters that we'll be using throughout. I personally, if you ask me for my knee-jerk reaction of what alpha means in the context of transmission lines or in the context of propagating waves, I will automatically say, oh, it's the attenuation. So again, this alpha and beta are actual symbols that we'll keep using for subsequent analysis. So let's plug that into our phasor plane wave electric field in the x direction propagating in the positive z direction. In phasor form, it would look like this, just like what I was talking about before. And so if you substitute this alpha and beta in, that's going to be equal to ex naught e to the minus alpha z e to the minus j beta z. So let's turn this back into instantaneous form. So first of all, let's see, what does this do? This becomes attenuation, right? So now my amplitude, because I have this alpha component here, my amplitude decays as I propagate in the positive z direction. And the rate of decay is this term alpha over here, right? In other words, let's put this back into its instantaneous form. So in the textbook, the instantaneous form, they sometimes use italics to describe, but another way to make absolutely known that you're talking about the instantaneous form is to explicitly specify that it's also a function of t. So how do we turn this into the instantaneous form? Remember, you multiply it by e to the j omega t and then take the real part, right? Now this is a real number, so this just comes out. This is not in the sinusoid. And then when you take the real part, everything that's in the e to the j's will end up being in a cosine, right? So going through that process, you'll find that the instantaneous form is going to be e to the ex naught e to the minus alpha z and then cosine of omega t minus beta z. So it's similar to the expression that we have for a propagating sinusoid. It's just if you have an alpha term, if you can write your jk as alpha plus j beta, you're going to find that alpha ends up being the rate of decay in your signal. So how do we relate this to physical material parameters that we know? So ultimately, this comes back to the permittivity being a complex number, as I described up here. Right? So if we write the permittivity epsilon as epsilon prime minus j epsilon double prime. So epsilon double prime is referring to the imaginary component. Epsilon prime is referring to the real component. Or another notation that you'll see is if we write it in terms of the relative permittivity. So a real relative permittivity minus j epsilon imaginary relative permittivity. If we plug this into our expressions for alpha and beta and also eta and k, we end up with the exact form of key parameters. So exact forms. So if you have a calculator, subsequently we'll be talking about different approximations that are less ugly, but in the meantime, if you have a fancy calculator and none of these expressions look too bad, these will always be accurate. So k is going to be equal to omega mu epsilon prime square root 1 minus j epsilon double prime over epsilon prime, and namely alpha, which is going to be equal to the real part of jk, is going to be equal to omega square root mu real part of epsilon over 2 1 plus epsilon double prime over epsilon prime squared minus 1 to the 1/2. Beta will look somewhat similar. So beta is the imaginary part of jk, and that's going to be equal to omega square root mu epsilon prime over 2 square root 1 plus epsilon double prime over epsilon prime squared plus 1 1/2. And then eta is going to be equal to square root mu over epsilon prime 1 over square root of 1 minus j epsilon double prime over epsilon prime. So these are exact forms of key parameters if epsilon was a complex number that you can use to in turn translate your epsilon prime and epsilon double prime into alpha, beta, eta, and k, which describe how the propagating wave behaves. Now you'll note that there's a lot of epsilon double prime over epsilon going on in the simplification process. And so this term here we often refer to as the loss tangent. And in the case of a good dielectric, that means that it's mostly real. So this epsilon double prime is going to be pretty small. And so if you apply the epsilon double prime over epsilon prime to be much less than 1, or that epsilon is about equal to epsilon prime, that it's mostly real, then you will see that this simplifies into the standard expressions that we're used to, where beta, or in this case, k and beta end up being the same if k is just, if alpha is equal to 0. So then you get beta is equal to omega mu epsilon, which is our expression for k, or 2 pi over lambda. And also the propagation velocity is equal to omega over beta, or omega over k, and eta is equal to mu over epsilon. So our more familiar expressions take hold. Now the other thing I want to do is tie the concept of a complex permittivity to conductivity. So what happens if we apply this complex value into our curl of h equation? So remember, the curl of h is equal to j omega epsilon e. So now j omega epsilon is now epsilon prime minus j epsilon double prime of e. And so you're going to get, if we expand that out, we're going to get omega epsilon double prime e plus j omega epsilon e. Now if we look at this, this is, in our Maxwell's equations, this is the displacement current, right? So then what's this? What's the remaining term here? If you think back to what the curl of h is in Maxwell's equations. That's right, this is equal to the current density, right? Or sigma e. And so what that means is that if epsilon is a complex number, in essence, you're going to find that the complex value of the permittivity is that these two are going to be equal. So the complex value of the permittivity is equal to sigma over omega. And so that is how this links to conductivity. And similarly, if you plug that in, you'll find that epsilon over epsilon prime, the loss tangent, is going to be sigma over omega epsilon. So this is the way that we can link the complex permittivity, epsilon double prime, to our concept of conductivity. Now before I want to wrap up, I also want to give approximations of these equations in terms of the conductivity, sigma, because quite often one of the pieces of information you have on the material might not be epsilon double prime, but you might be given sigma instead. So I'll just summarize the steps and then just highlight the results. I think that the details aren't that important, but the goal is to rewrite in terms of sigma, mu, and the real part of the permittivity. You'll also give in a dash of binomial expansion, something that is always handy to do when you have a square root with ugly things inside. And then also you assume that it's a good dielectric, so that the loss tangent for the most part is going to be less than 1. You end up with the following approximations. So you can write alpha as being approximately equal to sigma over 2 mu over epsilon prime. Beta is going to be approximately equal to omega over mu epsilon prime 1 plus 1 over 8 sigma squared over omega epsilon squared. Apologies, no square here. And then also eta is going to be equal to square root mu over epsilon prime 1 plus j sigma over 2 omega epsilon prime. So this is a set of rewriting of alpha, beta, and eta in terms of the conductivity, and it's valid for whenever you're working with the dielectric. So in summary, we started by looking at the dielectric term description for a phasor, and namely we said what happens if k can be a complex number. And what we ended up finding is that if you say jk is a complex number, alpha plus j beta, the alpha ends up being an exponential attenuation as the wave propagates in the z direction. And we link that to the fact that this term might be complex if your permittivity, epsilon, is a complex number. And when you do that, you plug that in, you come up with these kind of slightly uglier forms for alpha, beta, eta, and k. We next look at what happens if the loss tangent is really small. So if epsilon is mostly real, or in other words, epsilon double prime is really small compared to epsilon prime, you'll see that it boils down to the more standard dielectric formulas that we have. But separately, by applying this complex epsilon into the curl of H, we find the ability to relate the imaginary part of epsilon to conductivity. And so through that, we then, with some other mathematical tricks, we have this alternate way of calculating alpha, beta, and eta that's valid for good dielectrics. In other words, valid when the loss tangent, epsilon double prime over epsilon prime, is much less than 1, with a few math tricks.